Now we move on to our last chapter, chapter 7. It is a comprehensive chapter, so we're going to introduce a new type, or not really introduce, but we're going to using a new type of functions, parametric equations, and apply everything we learned from Calculus 1, Math 170, all the way to this class from the integrations at the beginning, finding the areas, the volume, surface area, arc length. So we're going to do everything here in section 7.2. So the first video, we're going to talking about the derivative examples. So the first question I have is, I have a set of parametric equation where x of t is t squared minus 3, y of t is 2t minus 1, and t is going to range between negative 3 to 4. And I want to find dt. I want to find dy dx. So this is the first derivative. So you can see that parametric equations, both variables x and y's are functions of the parameter t. You can also thinking about as the time. Then in order for us to find the dy over dx, the derivative, we need to apply the formulas or the chain rule. So dy dx is actually dy dt over dx dt. So what does that means is we are going to find dy dt from the y function, taking the derivative of y with respect to t, which is going to be 2. And dx dt, which is this function here, we're going to take the derivative with respect to t, which is 2t. Then we can replace them or plug in. We got 2 over 2t, which is just going to be 1 over t. Now that is our derivative dy dx. And if you're kind of interested about how the graph looks like, because we have the interval for t from negative 3 to 4, a quick sketch. The graph is going to look like a sideways parabola, has a starting point and then an end point. When the starting point starts, when t is equal to negative 3. When the graph ends, which is when t is equals to 4. So there is a path. So you can thinking about there is a particle starting from t equal to negative 3 is here, and then little by little moving, and then the way the particle is moving leave a trace, and that is the parametric equation graph or curve. So some other type of question we can ask you, since we're talking about the derivative, is the tangent line. So I have parametric equations. X of t is equals to t squared minus 3. Y of t is equal to 2t minus 1, which is the same graph we have. T is from negative 3 to 4. And I want to find the equation of the tangent line. Since we're talking about the equation of the tangent line or the slope, then we need to have a point when t is equal to 2. So we already got my first derivative, which is the slope. So the first derivative dy dx, which is the slope of the tangent line. So the slope at t equal to 2 is dy dx is equal to 1 over t, which is equal to 1/2. Now, once we have the slope, we need the equation of the tangent line. Then we also need to calculate what is x of 2 and what is y of 2. X of 2, which is going to be 2 squared minus 3, which is 4 minus 3, which is 1. And y squared is equal to 2 times 2. Y2 is equal to 2 times 2 minus 1, which is 4 minus 1 is 3. So what that means, we have a point. When t equal to 2 on the parametric equation, the point we have for that particular time is 1, 3. You can thinking about it is 1, 3, for example, this point. When t is equal to 2. Then using the equations, the point slope form for finding the equations, we have y minus y0 equals to m times x minus x0, which is going to be y minus 3 equal to 1/2 times x minus 1, which is 1/2 x plus 5 over 2. Okay, so that is the slope. And corresponding to the slope is the equation of the line. Equation of the tangent line when t is equal to 2. Now, since we talk about the first derivative, we can also find the second derivative or even higher order derivative. So I still have the same function. X of t is t squared minus 3. Y of t is 2t minus 1. And t is between -3 and 4. So I want to find the second derivative, which is d squared y over dx squared. So the second derivative is going to be the derivative of the original one. So this is, according to the not really the definition, but the way we define second derivative is the derivative d dx of the first derivative dy dx. And what is that means is d dt of dy dx over dx dt. Because we do not have d dx. So we have to rewrite it in terms of derivative of t. So pretty much we're taking the derivatives with respect to t. So we already know dy dx from the previous one, which is 1 over t. We've been using it for the past 2 examples. And dx dt, we also know from the previous calculation, dx dt. I mean, you can also find a derivative at this point too. So dx dt is 2t. Now, what is the derivative of the t with respect to t of 1 over t, which is the top portions? We can thinking about that is power rule with -1 as the power. So this is going to be -2 to the -2nd power. Combining them together, which is -1 over 2t cubed. And that is the second derivative.